Hello, my name is Max Tabago, and this is my Physics 2212 Lab 5. So in this lab, we're going to observe a magnet falling through an aluminum foil tube. We're going to model that fall computationally and then compare a computational model with observed data. Some fundamental equations we're going to use are the magnetic flux equation, which relate the integral of the electric field to the length to the inverse of the change in the magnetic field over the change in time, the change in magnetic flux equation, which is that flux is equal to the integral of the magnetic field times A in terms of A. And so in this case, it's just B times A, or the magnetic field times area. And Ohm's law, current is equal to volts divided by resistance, or V is equal to EMF is equal to the negative of the change in the magnetic flux over change in time. And so for our experiment, let me see. So here's a picture. This is probably a better slide to go first. The surroundings are the aluminum foil tube and everything else, table, earth, universe, etc., with the system being the magnet, and the initial conditions to drop the magnet through the aluminum with the north side facing down. And so the average time it took for the magnet to fall through the tube was 1.422 seconds. The height of the aluminum foil was 0.305 meters, and diameter was 0.28 meters. The magnetic dipole was 2.198 ampere meters squared. And I guess this is a little early, but yeah, our computational model showed 1.764 seconds, which was longer than what was true. And this was taken over 5 experiments. So here it is. So the time taken for the magnet to fall through, average of 1.422. With our magnetic dipole, here are the 5 different trials, and then the checkpoint questions. Why can't we use a Ferris tube? This is because Ferris tube will have magnetic properties, or in other words, it will itself turn into a magnet, whereas this aluminum foil won't. And what happens to the magnet? How does this compare to the magnet falling in free space? So the magnet falls slower than in free space because there's an upward magnetic field and therefore force induced by the current in the aluminum foil. And so this is the computational model. In the top, this is where we changed the constants, the length, width, mass in the UMag of our experiment, and then this down is a for loop that does the modeling, and then on the right here is our calculations. And so here are the results. The time in seconds was 1.319, and this graph got a little cut off, but it's velocity versus time is what this graph is showing. And so there are notable differences, but it is fairly close. And so actually, let me go over those differences first. So the differences are probably mostly experimental error. Human error and timing could be a big one, as well as adding force to the drop. It's hard to get a perfectly even drop, and then as well as time it completely perfectly. And then there's also some room for potential calculation error, wrong equation, math step, sig figs, etc. But more than likely, any difference is going to be human error and timing, or dropping the magnet, or external forces in the room, something like that. And then so, what if the resistivity of the conductor were reduced as close to possible to zero? How would the dynamics of the following magnetic change, reducing the resistivity can lead to larger induced current. So this would slow it down even more. Larger induced current is more force in the opposing direction. And then what if the holes or slots were cut into the tube? How would this affect the ring currents in your model? The holes can disrupt the ring currents flowing into the tube. And that's all the time I have. Thank you.